Welcome to Real Analysis P3, Relations and Equivalence Relations. Equality is useful, but sometimes it is far more precise than the problem deserves. A relation lets us declare when two objects are connected, and an equivalence relation lets us treat certain objects as the same. A relation from a set X to a set Y is simply a subset of the Cartesian product X times Y. Each ordered pair in R records one connection. The picture is merely the same information with arrows. We write XRY when the ordered pair X, Y belongs to R, and read it as X is related to Y. If X and Y are the same set, then R is called a relation on X. Less than, divides, and having an even difference are all relations on the integers. A relation does not promise that every object is related to something, or that the connection behaves politely. An equivalence relation is a relation on X satisfying three conditions: reflexive, symmetric, and transitive. Reflexive means every X is related to itself. Symmetric means that if X is related to Y, then Y is related to X. Transitive means that if X is related to Y and Y is related to Z, then X is related to Z. Omit any one of these, and the word equivalence becomes optimistic marketing. For example, less than is neither reflexive nor symmetric, although it is transitive. Less than or equal to is reflexive and transitive, but symmetry still fails spectacularly. Our main example is congruence modulo 3. X is related to Y when 3 divides X minus Y. Thus 1 is related to 4, -2 is related to 7, but 1 is not related to 2. Divisibility immediately verifies reflexivity, symmetry, and transitivity, so this really is an equivalence relation. For X in X, its equivalence class, written bracket X, is the set of all Y related to X. The element X is called a representative of its class, and a class usually has many representatives. In fact, related elements have exactly the same equivalence class. Modulo 3, every integer belongs to one of three classes, according to its remainder. For instance, bracket 1 equals bracket 4. 4 is not a new class. It is merely another representative. Here is the key fact: two equivalence classes are either identical or disjoint. If their intersection contains Z, then X is related to Z and Z is related to Y. So X is related to Y. Related representatives have the same class, so the two original classes are equal. There is no partial overlap. Equivalence relations do not permit the mathematical version of complicated friendship groups. A partition of X is a collection of non-empty subsets called blocks. The blocks cover X, and distinct blocks are disjoint. Every element belongs to exactly one block. Every equivalence relation on X produces a partition of X, whose blocks are the equivalence classes. Reflexivity puts every X inside bracket X, so the classes cover X. We already proved that intersecting classes are equal, so distinct classes are disjoint. That is exactly the definition of a partition. The theorem is not decorative terminology. It is the entire geometry of equivalence. Conversely, every partition defines an equivalence relation. X is related to Y when they lie in the same block. Being in the same block is reflexive, symmetric, and transitive, so nothing is lost in the translation. The quotient set X modulo the relation, written X/tilde, is the set of all equivalence classes. Passing to the quotient replaces every object by its class, deliberately forgetting distinctions that the relation declares irrelevant. Sometimes X has extra structure, and compatible operations descend to the quotient. For example, Integers modulo 3 inherit addition and multiplication by operating on representatives, then taking the resulting class. Thus bracket 2 plus bracket 2 equals bracket 4, which is bracket 1. But an operation on classes must be well defined. Changing representatives must not change the output class. Congruence respects addition and multiplication, so the modular operations work. Arbitrary relations and arbitrary operations may not. Whenever someone defines something using a representative, ask whether a different representative gives the same answer. Mathematics enjoys hiding traps behind innocent notation. To summarize, a relation is a chosen subset of a Cartesian product. An equivalence relation is reflexive, symmetric, and transitive, and its equivalence classes partition the set. The quotient set is the set of those classes, and compatible structure may descend to it. So an equivalence relation is not merely equality with a new symbol. It is a systematic method for deciding which distinctions to forget. That is all for Real Analysis P3.